Ibrahim Isaac, you can see the screen, right?
Yes, sir.
Yes.
So, so thoda bahut na we'll start a little bit transition metals, right? Remember, this was the only topic in inorganic in A levels. So the first thing is just basic stuff, which is where do you have? I mean, where do you have transition metals? So if you have your periodic table, they would be kitne 1, 2, 3, 4, 5, and there's 1, 2, 3, 4, 5. So there is a row of 10 elements, which is not actually your transition metals. They called actually something else. Uh, so इसके बाद कितने 4, 5, 6, 7, and 8. Yeah, that's what your periodic table looks like. And yep, acha. So this is group one. You have group two, okay? Or this one is obviously group 3, 4, 5, 6, 7. You get 3, 4, 5, 6, 7. So this is going to be another one, which is your final one. As anyways, they're not called 8, they're called 13, 14, 15, 16, 17, and 18, right? Now, the first block is known as your S block elements, these ones. These are called S block elements. These ones over here, they call your P block elements. And the ones that you think are transition metals, they are known as D block elements. You can remember these are technically these are not all of them are transition metals. Achha, why are they called S block elements? Because the last electron goes into an S subshell. So, for example, if you have uh, sodium, sodium has 11 electrons. So, if you write down the electronic configuration of sodium, that's 1s2, 2s2, 2p6, and then there is 3s with 1 electron in it. Similarly, if you so I'm going to tell you that the outer shell is for the group 1, it's always going to be S1. The outer valence shell for group 2 is always going to be, it's always going to end up with S2. Okay, so the outermost shell, remember, we're only interested, most of the time, we're only interested in the outermost shells. Mg is in group 2, so it's going to be exactly, it's going to end up with S2. And so is the case with P block elements because the last electron goes into. So group 3 will always be S2P1. 4 would always be, its outer shell would be S2P2. And so on, S2P3, then you have S2P4, then this is going to be S2P5. And then the last one is going to be S2P6. So if you pick any element, for example, sulfur, it's in group 6, it's got 16 electrons, so that's 1s2, 2s2, 2p6. Then you have 3s2, and then you have 3p4. So its outer shell is going to be S2p4. Sulfur was in group 6. So any element that's in group 6, it will end up in its outer shell, it's going to end up with S2p4. So the reason they're called p block elements is that the last electron goes into a p subshell. Okay. And that's the same reason why these are called d block elements. Because the last electron will go into, this is how many 1, 2, 3, 4, 5, 6, 7, 8, 9. So these elements, starting with, I'm just going to scandium, titanium, vanadium, uh, chromium, manganese, iron, cobalt, nickel, and then the iron, cobalt, nickel. Then you have copper, and then you have zinc. So hopefully that's the right order. I said so these ones over here, they're known as D block elements. I said so because the last electron would go into a D subshell. So if you look at scandium with 21 electrons, okay, so this is transition metals start at proton number 21. So this is 21, and then it's before the fourth period, there are no transition metals or D block elements. So 25, 26, 27, 28, 29, and 30. So I'm going to write down the electronic configuration of most of these. So scandium is, but not the complete. It's 1s2, 2s2, 2p6, 3s2, 3p6. Then it's 4s2, and then there is one electron going into a D subshell. Because remember, when you're trying to fill electrons according to the Aufbau principle, you fill the outer shell first, and then there are electrons going into a D subshell. Basically, what happens is that there are so many electrons in the D that it's easier for the electron to actually fill the outer subshell first, because slightly further away there's going to be less repulsion. I mean, the inner shell will be too crowded that it gets partially filled and you start filling the outer shell first, and then the inner shells again start getting filled up because it's easier for the electron to occupy the further away locations. I said, but anyways, you already hopefully know this. Now, after scandium, there's titanium. Let me just double check this. The order of titanium and vanadium. Scandium. Just one second. Let me just have a look at the periodic table. Scandium, titanium, vanadium. Okay, that's the right order. I said, so titanium would be 22. Everything will be exactly the same. It just has one electron extra. So the only difference is, okay, there's just one electron extra. So it's going to be the fourth shell will get filled, and then there would be two electrons in the inner D subshell. And this continues. So titanium, vanadium, you've got chromium, manganese. Okay, I'm going to write the electronic configuration of all them. Manganese के बाद क्या था? Cobalt, manganese, iron, cobalt, nickel, copper, and then finally you have zinc. So 23, 24, 25, and 30. Now, every time what happens is that the rest is the same. It's always going to be 4s2. And remember, the D has a total of 10 electrons. So every time, the outer shell kind of remains exactly the same for all of them. It's the D that continues to fill up. So it's going to be 3d4, then 3d5. There are going to be two exceptions. We're going to talk about them. 3d6. Then it's 3d7. After that, it's 3d8. Then 3d9. So you're crossing the row and the D subshell is getting filled up. And then it's 3d10 finally. Adjustment, there are two exceptions. And the two exceptions are that chromium and copper have a slightly different electronic configuration. So instead of 3d4, It is actually 3D5 and 4s1. Half-filled D subshells are more stable, and completely filled D subshells are more stable. So for copper, it's not 3D9, it's actually 3D10, and there's one electron less in 4s. So you have to remember that for chromium and copper, the half-filled and the completely filled, and this is an exception just for them. It doesn't really apply to anyone else. So for them specifically, the half-filled and completely filled electron D subshell is more stable. Basically, that's the electronic configuration they like to have. So copper would have been 3D9 4s2, but it's actually 3D10 4s 4s1. Okay, so you got to understand that you don't have to. I mean, it's easier. You just start. I mean, this is 3D1 4s2. This will be 3D2. So you don't waste time writing the entire electronic configuration. You know what the outermost electronic configuration is by just increasing the number of electrons in the D, and always remembering that there are going to be two exceptions, one at chromium and one one at the end at copper. Because you have to keep that in mind. So it has to be, you have to have a quick way of knowing what the outer electronic configuration of these atoms or elements is. And remember, the word for them is D block elements. These are not transition metals. Transition metals are, I mean, they're not exactly the same thing. They're almost the same thing, but not technically. That's D block elements. So यहाँ तक, is this clear that you've done with electronic configuration? Is that clear? It's okay, very
Yes.
fast. So the next thing is transition metals have like 4 5 properties. And I'm going to tell you what a transition metal is. First thing, not all D block elements are transition metals. Transition metals is a set of properties. If they exist, then it's classified as a transition metal. For example, zinc. Zinc is not a transition metal. So what's a transition metal? It's a few properties, and the element, if it exhibits any of those properties, you can kind of classify it as a transition metal. So what are those properties? Number one, this is what you did in IGCSE. They've got high melting points and boiling points. Number two, they've got high densities and sometimes really high densities, like 8 or 10 times more than water. Number three, which is very important, they're going to form colored compounds and complexes. Number four, they're very good catalyst. And number five is that they have variable oxidation states. So if your compound has any of those properties, then it's probably going to be a transition metal. So, but not all D block elements have those properties. So, which is why D block is a better word. Transition metal only applies to those that have those properties. The technical definition of what a transition metal is that it's so technically The definition is that it's an element that forms stable ions with incomplete d subshells. So with incomplete d subshells. Uh, so any element that does that, remember it has to form a stable ion, not just any ion. And when it forms those stable ions, the stable ions must have incomplete d subshells. Here, for example, and remember the definition is that the ion should be having incomplete d subshells. We don't care what the element is having. So for example, I've got iron. Iron has a stable ion which is 2 plus. It's got 26 electrons. I mean, so electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p, 3p6, and then it's 4s2 and 3d6. Now, when it forms a 2 plus, remember the electrons are lost from the outermost shell. So these electrons are gone. The iron ion has a stable ion and it has incomplete d subshells. This is incomplete. So that means iron can be, technically, it can be classified as a transition metal. Same is the case with, let's say, copper. The stable ion, copper actually has two stable ions. One of them doesn't really exhibit transition metal properties. So, for example, you got copper. Copper had, I mean, all of this. I mean, you can write the shorter version of the electronic configuration, which is what is the shorter version that up till this point, that's argon. So you can just write argon in square brackets. And copper was 3d10, 4s1. Now, when it forms an ion 2 plus, it's 4s1. So when it forms a stable ion, it's going to lose electron from the 4s and it's going to lose one electron from the d. And the d is incomplete. So that means copper is behaving as a transition metal. But sometimes it's not behaving as a transition metal. For example, if copper is 1 plus, that's another stable ion of copper. So if it's 1 plus, that means the outer electron is removed. And now its d is complete. So if it forms a plus 1 ion, then that means it's not behaving as a transition metal. It's not going to show those properties or not the entire set of properties. So not, so if it's plus 1, then it's not behaving as a transition metal. And we're going to discuss this in a lot more detail. That the reason they form colored compounds is because of this incomplete D subshell. We're going to discuss why much later on. So whenever something has incomplete D subshell, its compounds are going to be colored. Why are they going to be colored? That's a different story. But copper 1 plus, it's not going to have colored compounds. And therefore you can't classify it as a transition metal. It's the same reason for zinc as well. Zinc is also not going to form its compounds are white. If you talk about zinc 2 plus, it's got 30 electrons. Its electronic configuration would be argon followed by 3d10 4s2. Now, since it's 2 plus, its outer electrons are gone. Again, it's got a complete d subshell. So it won't form any colored compounds. So remember, zinc, although it's a D block element, it's not a transition metal. So no transition metal property. Okay, is this clear? Ibrahim, Ishaq, Qasim, is this clear?
Yes, sir.
Yes.
So remember, zinc is not a transition metal. So is scandium. Scandium is the first one in the block. Scandium is also not a transition metal, this one over here. Zinc is not a transition metal, so is scandium. Because the stable ion of scandium also is, the stable ion of scandium actually doesn't really have a D subshell to begin with. It's got 21 electrons. It's the stable ion is 3 plus. So its electronic configuration would be argon, followed by 3D 1, 4s2. Now, when it forms 3 plus, that means the D is gone. So it doesn't, there is no D subshell. Remember, we needed incomplete D subshell. So no transition metal properties. Especially colored compounds. I said that's one thing. Now, one by one, we're going to talk about now we know which one is a transition metal, which one is not a transition metal, and I'm going to mark it over here that that these two, the ones over here, that's zinc and scandium, and there are a lot more elements over here which are not transition metals. Yeah, but the top row is the more important one. So one by one, we're going to talk about their properties. The first property is they've got high densities and high melting points and high boiling points, and they've got variable oxidation states. So we're going to discuss one thing, which is that one by one. First thing is, why do they have high melting points and boiling points? And sometimes those melting and boiling points are really, really high. Like if I have the melting point of let's say sodium, kitna hota hai? Sodium is probably less than 100. As sodium is not even in the row, so potassium is the closest one. The potassium melting point is 63.5. Here, that's group 1. That's 63.5 degrees centigrade. And you have calcium then. Now, calcium slightly higher, I think 600. Calcium melting point is, it's other 842. Calcium is pretty high, 842 degrees centigrade. Okay, then if I go further down the line, so scandium, so now you have transition metals, right? Scandium, right next to it. Calcium is 20. Scandium, vanadium, titanium. So if I go to titanium, that's 1668 degrees centigrade. So it's almost it's almost double, twice as much as calcium. So they've got really high melting points. Iron is also, I think, higher. The iron, 1538. So iron is somewhere over here. So that's pretty high as well. Okay, so there's a significant difference. All of a sudden, you leave group 2 and you jump into transition metal, and the melting points are like really, really high. Okay, so what's the reason? The reason is that when you go across the period and move to the right, you get across the period. What happens is that you get more protons in the nucleus. So there's more nuclear charge. So there's more nuclear charge, which is why there is going to be more attraction for outer electrons. So there's going to be more attraction for valence electrons, which is why the atomic radius decreases. So the atomic radius decreases. And so if I talk about the atomic radius, there's going to be significant difference between the atomic radius of calcium with respect to, let's say, iron. So calcium's atomic radius, and let's talk about atomic radius alone. That's around 0.197 nanometers, right? Yeah, that's 0.197. And when I talk about the atomic radius of, let's say, iron, so that's around 0.126 nanometers. So basically, what happens is that the size of the atom of iron is much smaller compared to, let's say, calcium. Potassium is going to be even bigger because potassium has even fewer protons in its nucleus. Okay, this is 19, this is 20. Iron over there is 26 protons. So that's point number one, which is that the atomic radius decreases when you move to the right. And the second point is that there are more delocalized electrons. Okay, that's point number one. The atomic radius is decreasing. Point number two is when you move to the right, there are going to be more delocalized valence electrons. And why would there be more delocalized valence electrons? The reason is that in case of calcium, if you look at the electronic configuration of calcium, that's 20, that's argon. The 3D is completely empty and there are 4s, 2 electrons in the 4s. If you look at iron, that's 26. It's got 3d6 and it's got 4s2. Now, in the case of iron, for example, the case of calcium can only lose its outer 2 electrons. That's it. It can't lose more than 2 electrons, and the reason is that the immediate next subshell is completely empty. So it has to go really inside the atom to pull more electrons out, which would require a lot of energy. So in its outermost shells, there's just 2 electrons. In the case of iron, there are a lot more electrons. Like this is the outermost subshell, but there's very little energy gap between the two. So there are 6 more electrons available as well, which is why they also have variable oxidation states because of that. That you can pull electrons from the 4s, but it's not that difficult to pull electrons from the immediate next door neighbor as well. But not in the case of calcium. There's a huge energy gap. You have to jump all the way, go inside the atom, right in the inner shell, and then pull electrons out. So iron can have more delocalized electron as well. So there's little energy gap between 4s and 3d. So Fe is able to lose more than 2 electrons. Okay. Is this point clear? Ibrahim, Sar, Qasim, is this clear?
Yes.
Okay, so iron is able to lose more electrons. So I'm gonna come to the bonding now. Okay, why do they have high melting and boiling points? So first thing is calcium is bigger in size. So the giant metallic lattice for calcium would be it will be forming positive ions, and and its metallic lattice would look something like this. It is going to be all the metal atoms would try to lose electrons. So they're going to lose electrons, but not more than two. So each one would probably just lose, just say no lose here, two electrons lost, two electrons lost for this one, two electrons lost, two electrons lost by this atom, two electrons lost, and so on. So that's each atom barely losing two electrons. So that's calcium. Iron, on the other hand, same exact structure, except much smaller size. Okay, because of the 26 protons, there's going to be more attraction. So the lattice is going to be more tightly packed. There'll be smaller ionic radiuses, and there are going to be a lot more delocalized electrons. Because iron can lose electrons from the outer 4s, but at the same time, it is capable of losing more electrons as well from the inner 3D as well. So smaller ionic radius. Okay, this is iron. And it has more delocalized electrons. Hence, stronger metallic bonds. In the giant metallic lattice. Okay, so is this clear the first thing? Okay, why do transition metals have higher melting points and boiling points? ये clear?
Yes.
So ये been clear higher melting points, boiling points.
Yes.
ठीक है. अच्छा, so that's one thing. ठीक है, they've got atomic radiuses that are decreasing, and they've got so that's higher melting points. We can also talk about the higher density as well. So why do they have? I mean, it's kind of the same reason. Why do they have higher densities? So that's pretty obvious. I mean, because they're smaller, they're more tightly packed, right? So what is density? Density is mass over volume, right? Not proportion, it's exactly equal to mass over volume. So the reason they have higher density and their densities are like really, really high. I mean, for example, if I just Google calcium's density, so calcium density is 1.526 gram per. So calcium is 1.526 gram per cm cube, per cm cube. That's almost close to water. Iron, on the other hand, would be much higher. Iron density is 7 point, it's almost 8, 7 times, 7.87 gram per cm cube. I mean, there's a huge jump. Because there are a number of contributing factors why the density is higher. So the number one is, well, they've got smaller ionic radius, so that you can pack more of them in a much smaller space. So they've got smaller ionic radius. So more atoms slash ions can be packed together. And the second point is, not only more of them can be packed together, they also have a higher mass as well. Calcium is what? Calcium is Calcium has a mass of 40, right? Iron, on the other hand, has an atomic mass. If you just look at the protons and neutrons, it's got an atomic mass of, I think, close to 56. I mean, the exact average mass is around 55.8. You get rounding it off, 56. So, so the atom also has a bigger mass as well. Okay? Iron has more protons and neutrons. So, so iron also has greater relative atomic mass. So obviously the density is higher. You got two contributing factors. More of them are packed together. Thus, the atom also has a bigger mass as well. So that's why they have higher density. You be clear why they have higher density. Is this clear, Isaac? Ibrahim, is this clear?
Yes.
Okay. And there's one more, which is we already discussed. Why do they have variable oxidation states? So we've kind of already talked about it. So three properties are already done. So why do they have variable oxidation states? Why not calcium? So we already talked about that. So so argon, then 3d04s2. So huge energy gap between the 4s. So a lot more difficult to remove electrons. You go all the way in. So you can't remove more than 2 electrons. In the case of iron, we already discussed this. You got argon, and then there is 3d6 and 4s2. So you can remove the outer electrons, you can also remove the inner electrons, not a huge energy gap between the two. They are very similar, very close in energy. So they have a small energy gap. So it depends on the other atom. If the other atom can pull electrons out of iron, iron would lose the outer electrons. But if the other atom, like you got a very electronegative atom, can pull more electrons out of it, electrons would also come out from the inner 3D as well. So iron can lose 2 electrons, it can also lose 3 electrons. It can lose more than those electrons as well. So small energy gap between 3D and 4s. So electrons can be lost from both subshells. So there's room for them to lose a lot of electrons, which is why some transition metals have +7 oxidation states as well, because there are a lot of electrons available. So it all depends on the other atom. How many electrons can it pull out of it? Okay, so a lot of transition metals have a lot of oxidation states. Okay. Jada, clear, we're done with 3 points. Okay, we know why do they have high melting points. We know why they have variable oxidation states, and we know why do they have high densities as well. Okay. So clear? Is this clear?